HTTP is the backbone of the modern internet. It powers nearly everything you see on the web. But do you really know how it works under the hood? Let's understand how HTTP and its underlying protocol TCP operate. Before we start, let's try to make a HTTP call via curl and analyze what's happening. Curl is a command line tool which can help us make HTTP requests. The -v flag here denotes verbose mode, which logs extra information like headers along with the body. Once we run this command, we see curl connecting to the server with some default headers. The server sends back the response, curl outputs it back to the console. Now, if we analyze the request, we can see curl sent multiple headers to the server, which included HTTP verb, which is get, the URL, which is / HTTP version, hostname, user agent, and accept headers. These details will change depending on what type of request it is, what sort of browser it is, and multiple other factors. Once the request reaches the server and it processes it, it will send back the response to the client. The curl will capture the response and log it. The server responded with some headers, including the protocol, the server, which we might not always see, date, content type, content length, and last modified. We can also see the actual body of the response, which in this case is HTML content. Upon successful communication, the connection is closed and curl exits. Curl helped us to see the entire request response process in the HTTP flow. Now it's our turn to see how curl does this task. In the previous video, we learned that simple looking functions are actually syscalls under the hood, which we discovered by breaking down the print function. We'll do a similar activity here, but we don't have to dive into source code or assembly to see syscalls. Instead, we can take help of a tool called strace, which is short for System Call Trace. strace logs any system calls that are made by a program, which helps us to see how curl program is talking to the HTTP server. It uses ptrace under the hood. We'll just prepend our previous curl command with strace and run it. Curl will then do its job and strace will log all the syscalls in the process. That's a lot of syscalls, but don't worry, we'll go through this together. We can see execv, which is a very special system call invoked by the shell during the fork process. The shell first forks itself and then uses execv to replace the child process memory image with curl. We can cover this in depth in the later videos, but it's not directly relevant to the network behavior. Similarly, other syscalls like brk, mmap, access are not relevant to our investigation, so we can skip them for now. Now that we are focusing on the interesting syscalls, let's start with the socket syscall, which asks the kernel to open a network socket and return the file descriptor to the application. In our case, we see 5 as the file descriptor returned to the curl. Any resource that we access is represented as a file, which we can perform input and output operations on. We'll use this file descriptor throughout the current run. The parameters that are passed to syscall, AF_INET is denoting IPv4, SOCKSTREAM denotes a connection-based protocol as opposed to a connectionless datagram protocol, and IPproto_TCP denotes TCP protocol. Next, curl makes some write calls to the standard error. Then, we see the connect syscall, passing our previous file descriptors created from the socket call, along with port 8000 and the address of localhost. Then curl blocks itself on the receive from syscall, and once the kernel gets the response from the server, it sends it back to the application. Curl gets the response back, it dumps the headers to the standard error and the actual body to the standard output, followed by the closing of socket and exiting the curl program. The summary of this activity is HTTP request is essentially opening the socket, connecting to the server, sending headers, receiving headers, the body, and cleaning up. Pretty straightforward, right? Since now we understand HTTP1 protocol, we can emulate it directly over TCP. To accomplish this, we'll use netcat, which can help us make TCP or UDP calls to any server. Let's connect to the server using netcat, and in order to send the data, we can use the standard input. The responses will be written back to the standard output. Let's add the HTTP headers here to pretend as if we are a HTTP client. HTTP headers are marked complete when there are 2 consecutive new lines. So once the headers are returned to the standard output, we can press enter twice and wait for the server's response. With just the right headers, we successfully emulated HTTP1 over TCP. Since the kernel TCP stacks handle connection management and networking for us, we can easily build high-level protocols like HTTP on top of it. But it would be even more fun to see how TCP works internally, giving us the complete picture. To help with that, we can use next tool in our basket known as TCP dump, which can capture, analyze, troubleshoot network traffic by displaying packets that pass through system's network interface. Let's start capturing packets via TCP dump. The -I LO flag helps us to listen to the local interface, while the -N and -X flags are here to tell TCP dump not to resolve host names and to capture the complete packets in hex format. We don't have to worry too much about them right now. We can trigger a HTTP request in parallel, and once we get back the response from the server, TCP dump will write the captured packets to the standard output. The output might look scary, but stay with me. This is a super fun part of the video. We'll inspect the packets one by one and analyze them. But before we can make sense of this raw data, we'll have to understand the structure of the packet and also how to track the overall flow. We'll attach two different views on the screen. The view on the left side is the packet view, which we can expand anytime. We also have the data flow view on the right hand side, which we can also expand. It shows the interaction between the client and the server. So, without further delays, let's jump on to the first packet. We can see this packet is sent from port 38908 to 8000. The client port is randomly selected. In this case, it's 38908 and the 8000 is the server port. We can ignore the flag options and the length metadata for now and directly jump to the raw packet view. Starting on the top row, we are seeing the layer 2 Ethernet headers. It consists of the destination MAC address and the source MAC address. These are the physical addresses of the machines. Since the server and the client both are on the loopback interface, these addresses are zeros. But in case of actual packets, you would see machine's MAC address and your router's MAC address here. Talking of addresses, how addresses are resolved and the packets are forwarded physically is an interesting topic on its own. But for now, we'll focus on the main agenda. Apart from the MAC addresses, we also see the Ethernet type, which consists of 0800, denoting IPv4. The next header that was added to our packet was the IP header. This is from the layer 3, which consists of the IP version, which is 4 in this case, and the header length, which is 5x4, that is 20 bytes. We also see a bunch of other data here, like length, ID, flag, TTL, checksum, source, and destination. Source and destination are particularly interesting here. The address starting from 7F is actually localhost, but in the hex format. Next header we have is the TCP headers, which consist of multiple different values. What is particularly interesting is the sequence number, which is generated randomly by the client, and the acknowledgement number, which is 0, since this is the first request. We also have the source, which is 97FC, denoting 38908, our client port, and the destination, 1F40, which is denoting the port 8000. We also have the flag, which is 02, which is the SYN flag. We also have MAC segment size, selective acknowledgement number, timestamp, and window scaling factor, which we can skip for now. So, all in all, the summary of this TCP header is that we are sending data from port 97FC to 1F40, signaling SYN flag. Now if we check the data flow view, we can showcase our current flow like this. Moving forward to the next packet, we can again open it in our packet view. In this, the Ethernet layer is same as before, and the IP layer just has the ID and the checksum changed. What's interesting here is the TCP layer, which has the source and the destination ports reversed because now the source is the server while the destination is the client. The sequence number again is randomly generated by the server, acknowledging the client sequence number. We also have the flag, which is set as 12, denoting the SYN ACK. So in summary, this is the SYN ACK back from the server to the client, which we can see in the data flow view. Moving on to the next packet, we can see the flag is 10 as the acknowledgement to the server's sequence number. After the client acknowledgement, we concluded our three-way handshake, signaling the connection is established and the client and server are ready to communicate. Moving on to the next packet. This time we also have the data populated in the packet. We can see the source port as the client and the destination as the server, along with the HTTP headers sent from the client to the server. So in the data flow diagram, we can see it as a GET request to the server. Next, the server acknowledges the headers sent by the client. And then server responds back with the headers. Once the client receives the headers from the server, it sends the acknowledgement back. Then the server sends back the actual body to the client, which client again acknowledges the server for the body, and then the server sends the FIN request to close the connection. Then the client acknowledges the FIN request, and at last the server closes the connection. So to summarize, what we just witnessed was a complete TCP and HTTP exchange from the connection setup to teardown. It started with a three-way handshake from the client sending the SYN request, the server responding with the SYN ACK request, and the client acknowledging with the ACK. This established the connection. Then, the client sent the HTTP request headers. In this case, it was a simple GET request. The server acknowledged it and then responded back with the HTTP headers followed by the response body. Finally, both sides gracefully close the connection using the FIN ACK flags. That's how even the simplest web request unfolds behind the scenes. Intense, wasn't it? But it's amazing how the things we use in our daily lives have so much of details behind them. Thank you so much for your time, and I hope you learned something new from this video.